Hello, class. Welcome to chapter 13. We're going to look at statistics and why statistics is so very important to the processes of research, specifically experimental research. So, when we're looking at statistics, you should have already taken your statistics class if you're taking experimental psychology. And statistics are used to quantify measurements of a sample and provide a numerical value to describe some particular significance or no significance between variables. So let's talk a little bit more about what that means when we're creating quantifiable measurements of samples to create statistics. So we have different types of statistics. We have statistics that actually describe samples with central tendencies and variability, which we call descriptive statistics. And then we have inferential statistics, which is going to allow us to draw conclusions about a parent population from a sample. So in your textbook, it talks about detective cats. And detective cats, when you look at that story about Miss Adams, detective cats can at best show that Miss Adams is probably guilty. But in statistics, we cannot necessarily say exactly or for sure whether or not there is an effect per se, but we can say that there is a significant probability that the independent variable had an effect or impact on the dependent variable. So while we cannot prove that definitely that is the cause, um, that from the independent variable that changed the cause, like I said, we can definitely always talk about probability, and that is going to provide us to our conclusion. If there is a strong probability or significance of the IV making some type of impact, effect, or change on the DV. So within our statistics, we draw our conclusions by creating a sample from our population. So we talked about this in the previous chapters, but essentially we want to draw a sample from the population that we are studying so that we can get representatives within our study to represent the general population so that we can take that information that we've learned within the study with the statistics and apply it to others um, in that population. So, for an example, if I'm doing a study on um, freshman students at an HBCU, then I would pull out of 100 students, I might pull in maybe 50 students to represent the 100. And from that sample, I should be able to make inferences as to whether or not um, the IB has an impact on the DV and use them as representatives. So, in essence, the population is the general population, and the sample is portions of the population that will represent the population overall within the study. So, in order to create these inferences, we use what is called a statistical inference. The statistical inference is the process by which we make statements about a parent population based on our sample. The differences in scores obtained from separate treatment groups are not significantly greater than what we might expect between any samples randomly drawn from the population. So, when researchers report the outcome of a study, it means that there was no treatment effect or effect between the IV and the DV. So, for a set of dependent variable measurements, there will be some level of variability within our scores. So this is going to show that our scores are different and that they are placed across the board within the distribution. So variability means that our scores are spread out and we see changes within the population of scores within the sample. So when we're looking at the significance, we want to determine whether or not we are going to reject or accept our hypothesis. So when we look at the null hypothesis, which is emphasized by the H and NO, this is going to be your statement that is going to um, make the inference that there is no significant effect from the IV onto the DV. Okay, that there is no significant effect or impact from the IV onto the DV. That represents the null hypothesis. So when you think of null hypothesis or you think of null, just think about no, using the word no. There is no significant difference between our variables, our IV onto our DV, null hypothesis. So results are statistically significant when the difference between our treatment groups exceeds the normal variability scores on the dependent variable. So we use what is called alpha levels, and these alpha levels are already set, but the alpha levels give us the values that are going to create the statistical significance, means that there is some type of treatment effect between the IV and the DV. So we have these two set alpha levels, which are 0.01 and 0.05. We typically do not shift higher than 0.05 for our statistical difference or alpha level. Then we also can look at alternative hypothesis, which is represented with H1. It is the statement that the scores came from different populations. The independent variable significantly affected the dependent variable, but we may have alternatives. So if I'm looking at gender per se, I might say that males have an impact on, well, let's just do maybe classification in college. We may be looking at freshmen versus seniors in academic excellence. Okay, so I may have one HO, and then I may have an alternative hypothesis to the significance, and then there is a significance. So no, there is no significance, and alternative, there is a significance. We may reject the null hypothesis when the differences between the treatment groups exceed the normal variability in the dependent variable at our chosen level of significance. So if we reject, or if you see a higher level, this means that there's no level of significance, or reject the null hypothesis and state that, there is a significant difference between the variables. So let's talk about our frequency distribution. The frequency distribution is going to show us how many times our scores in our distribution has shown. So the frequency distribution displays the number of individuals contributing to a specific level of the dependent variable in a sample, and how many times we actually see those particular scores show. So if I have 3, 4, 4, 4, 8, then our 4, I have 4 that happened 4 times, and I may have 3 that happened 2 times, and I have 2 that happened 1 time. So that is the frequency scores across the distribution, how many times the score is shown. So the values of the dependent variable are indicated on your x-axis, while the frequencies of these values are going to be shown on your vertical y-axis. You can calculate the number of participants by adding the frequencies together. So the decision to accept or reject the null hypothesis typically depends on whether the differences we measure between treatment groups are significantly greater than the normal variability among people in the population. So, in essence, the greater the normal variability in the population, the larger the difference between groups required to reject the null hypothesis, or to say that there is no significant difference. So we may create a directional hypothesis. This is going to state that we're going to pick a side. We're going to predict the direction of the difference between the two groups on the dependent variable. So for an example, I might say that the experimental group will lower their systolic blood pressure more than the control group. So let's give a better example. I might say that um, um, freshmen will have a higher score when taking an 8 a.m. class versus freshmen who take a 6 p.m. class. Okay, so I have created a direction on my hypothesis. I have given the direction of which I think is going to go, that freshmen are going to do better, versus saying, is there a significant difference between um, classification and academic performance? I'm going to say, yes, there is a difference, and this is the difference. This is going to create the direction of the hypothesis, and I, as the researcher, can predict that outcome, which will create the directional hypothesis. A non-directional hypothesis is going to predict the two groups that will have different values. So again, if I'm not going to choose which way that is going to go, then that will be the non-directional hypothesis versus directional. I'm going to answer and predict and choose the direction that I think the outcome will be for the hypothesis that I've created based on my research question. So we've talked about the alpha level, the significance level within our statistics. And the significance level is our criterion for deciding whether or not we're going to accept or reject the null hypothesis. So again, psychologists typically will use a significance level larger or lower, 0.05 or 0.01. We will never go larger than 0.05 alpha level. The significance level of 0.05 basically means that the pattern of results is so unlikely that it could have occurred by chance fewer than 5 times out of 100. So we never go higher than that number to state our significance between the variables. So we have type 1 and type 2 errors. When you look at a type 1 error, this is when the researcher rejects the null hypothesis when it is correct. So I might reject it and say that there is a significant difference when there actually is no significant difference. So that is rejecting the null hypothesis when it is correct. Whereas a type 2 is error is the opposite. So I'm accepting the null hypothesis when it is false. So I'm saying that there's no significant difference when it actually is a significant difference. And that is the differentiation between a type 1 error and a type 2 error. The American Psychological Association, you know about them, the APA, they have created a task force, and that task force has recommended that researchers include estimates of effect size and confidence intervals into p values. Okay, when you calculate a p value, that is statistically significant. This means that your results are unlikely to be due to chance, but actually that it probably really is some type of significant effect or impact from the IV onto the DV. The effect size definitely matters. The effect size is going to estimate the strength of the association between the independent variable and the dependent variable, and the percentage of the variability in the dependent variable, and it is due to state that it is due based on the independent variable. The confidence interval is going to be a range of values above and below the sample mean that is likely to contain the population mean. So usually 95% or 99% of the time, the confidence interval will show that range of values that are going to fall below and above the average scores within the sample. And then we have the critical region. The critical region is the distribution that goes outside of the extremities of the normal population curve, the normal curves, the bell curve. And we're going to show an example of that in just a minute. So for an example, if our criterion is 0.05 level, the critical region consists of the most extreme areas, 5% of the distribution that lends itself on the outside of the normal distribution. And here is a picture of this. And we're looking at a two-tailed test, which is right here at the top, where you see in shaded in blue, which would be those critical areas. And then at the bottom image is going to be a one-tailed test, where you see on that one side where you have that critical region. So to reject the null hypothesis, the test statistics will fall to within the shaded critical region areas outside of the normal distribution. So the differences between a one-tailed test and a two-tailed test. A one-tailed test has a critical region at one tail of the distribution, as we saw in the illustration, the previous illustration. And we use a one-tailed test with a directional hypothesis. In a two-tailed test, you guess, right? It has two critical regions on both ends of the distribution. And this lets us know, that we use a two-tailed test for a non-directional hypothesis. Inferential statistics allow us to predict the behavior of the population from a sample size. So examples of inferential statistics are the t-test and the f-test. The t-test is going to be a simple test that looks at the significant difference between one IV with two levels and how those may or may not impact one dB. Or f-test is like having a test that is used for a broader scope of variables. So I may have two or three independent variables that I'm testing on to maybe two different dependent variables. So if I have a larger sample size and I have a larger variable size to test, then um, I would use a more sophisticated test, such as the f-test versus the t-test. So if you think about the differences, the t-test could be described as like a flip phone, and an f-test can be described as like an iPhone 50 or iPhone 15, excuse me. So one is a little bit more sophisticated to handle a larger size of data information. And that is going to conclude of why statistics is important. I will see you in the next lecture.